new video, new challenge. Today we're stepping into another dimension of transformers that involves imagery data, specifically that has to do with the vision capabilities of language models. And yeah, those are the multimodal models that have it, okay? And this thing has been gaining quite a bit of traction by the notion that big AI vendors have introduced it to their products, and you can already go ahead and use it. There's ChatGPT Vision by OpenAI, there's Gemini by Google, where you can upload a photo or even a video now and have a conversation with chatbot about it, asking questions like what it sees in the video, and can even you can challenge it to reason about things. But the spoiler alert, those are the same transformers that power it up. It's just that they are done in a bit of an intricate manner in a tricky fashion, so to speak, so that they accept those multimodal inputs. And today we're going to be looking into some of the recent research, some of the open source models that are available out there for you to use. And I'm going to teach you how exactly they do that. So we know where is it applicable to leverage that and what really you need to know before you go after it. On today's agenda, there are a couple of items we're going to go through, and we're going to start with the coolest stuff, the most recently released multimodal models that have this vision capability, and by some of the big names such as PaliGemma by Google, 5.3 Vision by Microsoft, but also this Pegasus 1 by 12 Labs, which is a video model. Actually, it even accepts sound and voice. So we'll see the capabilities of those, but our mission doesn't end there. It's just to get excited a little bit about that, but we really want to understand how they function. And in order to do that, we're going to go through a brief recent history of various vision language models. There are long survey papers and all, but I promise to keep it short, just to highlight some of the important items, just to underline some of the key points with a purpose to explain to you the core principles of how those models function, how they fuse data, how they align data of different modalities, and what kind of output they provide to align with your expectations. We're also going to look into some of the tools and methods helpful to work with a model above within the context of specific tasks. And lastly, the most exciting part probably, I'm going to demonstrate to you how I analyze the video footage I've taken with these smart glasses of mine. These are the Ray-Ban Meta smart glasses I've just purchased. So they have little cameras on them so they can kind of walk around and film the world. To demonstrate to you model capabilities, I'm going to take that footage through some of the video models to get some insights, and you're about to see the functionality of those models in the wild. And the first on our list is a highly capable multimodal video model, Pegasus 1 by 12 Labs. They've just released it to open beta in the month of March. So everybody can go ahead and try it. There is a web version of their thing. We can insert the video, upload it, and it'll give you a descriptive summary of that video. But it also accepts your prompt, and it also takes into consideration an audio on that video. Okay, so given all together, it'll generate a descriptive summary of that video, but it will also try to find certain moments in the video depending on what you're prompting about, and it'll extract that information, give you the timestamp ranges so they can, cut the video and extract a certain piece out of it, and it'll give a corresponding summary related to that particular part only. The high-level architecture of this model is pretty much straightforward. It consists of three main parts. The video encoder model, which takes your video input along with the audio in it and generates rich embeddings, which are representative of information in the video frames. Okay. The second portion here is the video language alignment model. That one makes sure that those embeddings of different modalities are aligned with each other. Basically, certain pieces of embeddings are correspondent to a particular place on the timeline, to a particular frame, so to speak. The third part is a large language model itself, as we know of, that takes all of those embeddings along with the user input embedding, and it provides the descriptive summaries in the form of a text, whether it's a summary really or an answer to a user question. It's up to the user prompt. They provide with some level of details how they've done the training, and it's been quite a challenge for them, I would imagine. They say there's a typical data scarcity when it comes to high quality video data. So they had to take not annotated video footage, and they probably implemented some sort of a pipeline that augment human capabilities powered by LLMs of sorts. And they've annotated more than 10 million diverse videos with highly detailed descriptions to train their model. They would include things like, activities in those videos, like, object descriptions, specific names of those objects, specific technical terms, and all those things. It's typical to training these models, the way they outline the procedure that their model had to undergo. It consists of regular two phases, a pre-training phase and instruction tuning phase. And during the pre-training phase, they initialized a regular video encoder and large language models. But we don't know the names of those entities. They never mention it. That is to say that their model is proprietary one, right? They never release the weights, they never release the details. The only way to kind of interact with it is through their interface and API, and this is something you have to deal with. But we'll learn about the ways to train those model in a second, okay? They also never mentioned the kind of pre-training objective, also kind of important. In the second phase, they do a regular instruction tuning. It's just to align the model outputs with like user expectations based on their prompt. The rest of the paper is just about the results, showing that their model has outcompeted competitors, both open source ones and proprietary ones like Gemini Pro, in the number of nominations on correctness, detail, context. They've mentioned specific benchmarks that they've used to evaluate the model and compare against the other models we've seen above. There's video conversation benchmark, zero-shot video question answering, video summarization, temporal understanding. And they also provide the links to their sources. The rest of the paper is all about models' capabilities, which are quite vast. That's why they dedicate the 70% of the paper to it. But we'll see there's like a lot of visual information too. They test the model in various use cases, in various contexts for real-world knowledge, video-based reasoning, 3D spatial understanding, temporal reasoning, and visual referring prompts. For instance, they're challenging the model to detect a place. That's a typical real-world knowledge test to see whether the model has been trained on enough data incorporating that very geographical information. So given the video footage and the prompt asking for location, the model is supposed to respond with that, okay? But here we see that the user is also asking to give a rationale behind choosing this very place. So amongst three models tested, Pegasus 1 and Gemini, Pegasus has given pretty much comprehensive answer. There's a name of a place, the information of a rationale and the coordinates. Gemini 1.5 Pro has given that key information without much rationale. It's like very concise here, but probably not wrong. And whereas like Gemini 1.0 has gotten it completely wrong. There are more interesting examples, and you can even like think of it like what you can like use this model for. Okay, there's a video-based reasoning to predict the future events based on the existing video footage. There's one for video-based reasoning, basically challenging the model to give an evaluation of a real estate property. There is a cooking challenge to ask the model to provide with a specific set of steps to prepare the meal. In this case, they are prompting it to describe the video in detail. Could have been a bullet point list or something. So in this very instance, the Pegasus 1 gives a very detailed kind of instruction description of that very video, whereas like Gemini preferred to stay brief and concise. So this is interesting. They have it well done. It's very well covered in the docs, the way how you use their platform. They have SDKs for Python and JavaScript. You can operate with their model through the API. They have some guides to cover different tasks, which you might want to do with the model. Okay. Pretty interesting project. Unfortunately, though, it's closed source, so we only can know so much about the details, how they trained it, what they've done with the model, where it's hosted, how much compute goes to serve the model. Those are very interesting questions, so let's dig a little deeper. PaliGemma is the latest Google's multimodal vision language model. It's inspired by Pali 3, basically following the same architecture. Pali 3 is another vision language model with 5 billion parameters, and it's been the path of scaling sort of. There is a SIGLIP image encoder that they've scaled up to 2 billion parameters, and it started showing much better multimodal benchmark results, specifically targeting localization and visually situated text understanding. What the model does is a few things. It can do a deeper analysis of images, provide insights, can give you captions of images, even short videos. You can send some short videos, no long ones, because the context window is limited because the model is moderately small, okay? Can detect objects and can also read text within the images. In the model card section, they provide with additional details about model architecture, what they've used for text decoder and image encoder, information about inputs and outputs, the data sets that they've used for training and fine-tuning. And they also give a bunch of evaluation data points in different task categories, such as image captioning, see here, question answering, some information about that, segmentation, and even video tasks. The model is open source, and that means that it's available for you to download to your local environment where you're going to be doing inference, and you can even like fine tune it if you will. It comes in a number of checkpoints available in the Hugging Face registry. The number in the end signifies the maximum resolution of a picture you can send to it. If the picture is bigger, you have to crop it or compress it, make it smaller up until that would fit that very dimension, square dimension. The JAX suffix means that the model is compiled for this JAX library that's efficient for TPU inference that's popular in the Google ecosystem. And the mix suffix means that they've trained the model the mixture of academic data. You can try those different models and see what works better for your particular case. And if you follow the link and scroll down a little bit, we'll see a typical usage of this model. It's a very simple code snippet. We've kind of gone through it already in one of my previous videos. They add additional feature for image processing here, though. There's a Python library PIL for working with images in Python. They download this image. In fact, they download the model's checkpoints. So instead of the model tokenizer, they are downloading the processor. Processor does more than just a tokenizer. It works with the images, right? So here how they prepare the user prompt. They take the prompt and the image through the processor, and that's going to be one model input, sort of like a one vector of everything, okay? And they're gonna send it through the model generated typical standard function of a model to process it, basically, right? They crop these, like, remember that video? They crop this like initial sequence out, leaving just what's new, what's model generated, and they decode it through the same processor to basically print it out what the model come up with. As per Microsoft's model, I already actually used one in my transformers research, where I trained it, fine-tuned it on a specific grammar data set, with it showing outstanding results, beating all of the other models participated. So just recently, less than a week ago, they've added this additional capability, additional modality to it, and they call it Phi-3 Vision. So this thing understands images now that come along with a text input. It could be multiple images, in fact, in a singular request to the model. It can extract text data from images. It can reason about what's happening in the images. It can even like process charts and diagrams, which I'm so willing to test it with. So they're providing with one example of such. There is a chart and asking the model to create a report about this chart. And the model is analyzing the data in the chart and providing with some of the insights about it, which is quite interesting. Since it's open source model, it's available for you in the regular Hugging Face registry. That's their model card, specifying a few checkpoints for different versions of their models. But the one that we are interested in is this one in the bottom for the vision model. For that one, there's only one checkpoint available for now, Hugging Face specific. So it'll work, but if you want a more kind of better optimized version for running in production, you want to aim for ONNX runtime, and I believe they're actively working on it because they've introduced it for all their other models. So it's coming, and definitely reach out to me if you need help to set up this thing, okay? If we scroll down even further, we'll see typical use cases we've already discussed. There's information on how to prepare for local inference. There's a chat format. If you want to like fine-tune the model, you have to stick to it. Okay. And simple example code, which is not very different from what we've seen with the Gemini, just that they use the, in fact, chart interface. So there's like a bunch of messages, user assistant messages, and there's like special tokens signifying the image position. So remember I said you can upload multiple images, can send for inference multiple of them in a single request. So the processor takes an array of those, and you need to specify the image indexes as special token names inside your prompt, so the model treats them properly. Okay. And then you take it all through the generate function, specifying some additional arguments if you want. You process the output, and it provides you the response in the form of a text. As per the tasks or what to use those vision models for, Hugging Face gives you some guidance of possible use cases where you can apply various vision models along with the data sets. It provides you with that information as well if you follow these links. But not all of these tasks, I would say, are quite vision specific. For instance, image generation and video generation aren't quite vision challenges, really. It's more like a Gen AI. It's more like a stable diffusion thing, which is another category of models, okay? The transformers section of the Hugging Face contains specific guides with good examples and walkthroughs for some of those use cases, some of the tasks. There is one for image classification, image segmentation, there's video classification, object detection, zero shot stuff, depth estimation is also quite a challenge. I'll skip this one, a mask generation and feature extraction. Those are all attributable to vision specific models. Let's just break down this one because I think it's interesting as it's video related, right? What does it mean to classify a video? Well, it simply means to assign a label or a class to a requested video clip. And the way they do it is they fine-tune an old vision model where researchers has done some magic to it, masking video clips, making use of supervised video pre-training, and it showed it achieved some impressive results on smaller data sets, some terrific results really using some older standard technology. So, but anyway, they fine-tuned this thing on a video data set that has like labels and stuff, and then they simply test it to show that it works. So if you go down, there's a bit of a data preparation, data processing stuff. You gotta organize the files the right way. You're gonna put them in proper folders. That's a data set, in fact. And the folders would signify the labels of the videos, and that will go into fine-tuning the models. You gotta specify proper paths so the model understands where to take the files from, assigning the labels so that it also kind of pays attention to the labels and learns. Here they define some constraints because you can't send very long videos or videos of high dimensionality. So they basically limit it. They also define the sample rate, FPS, and they normalize the videos to the standard settings for the model to work with. Then they're preparing for the model training, for which they're using the same classes as for regular text-only transformers. Hyperparameters you want to consider, they could be very specific to this very model. Can probably look up some of the recommended values in the research papers if researchers have identified those, or you can just experiment to see what works better. Okay, then they define the metric that's for reporting purposes. They define the data collation function to prepare the data to send to the trainer, and then the regular trainer class, specifying all of those things above, and they finally kick off the training job. And the task comes down to inference, for which they are downloading the model, the fine-tuned version of the model into the pipeline. So they defining this class, and they take one video through it, okay? They're sending this video to request the model to identify the class, one of the known labels from that data set, and it identifies with a 92% of probability that the action here in the video is a basketball dunk. There is another class of tasks Hugging Face differentiates in their documentation, and they call it multimodal. There are a few of them present in this guide for image captioning, document question answering, and visual question answering. This last one, text-to-speech, doesn't quite attribute to the vision class of tasks, so we'll skip this one. For the simplicity's sake, let's review this very first image captioning task. And we've kind of come across it already before. Image captioning, what does it really entail? So it simply gives a descriptive text, a caption, so to speak, to an image provided, or it could be a video, all right, as we've seen with Pegasus 1. So for this very challenge, what they do is that they take the data set of Pokemon images, accompanied with descriptive captions here, a label, so to speak. For that very task, they took Microsoft's Git-based model from 2022. I found the paper with it, where they simplified the previous architecture, leaving just one image encoder and text decoder. They improved the data quality, increased data size for pre-training, and it all kind of showed much better results, much better performance. As per the diagram, as you can see here, it's like pretty much straightforward. There's no like cross attention, there is nothing like that intricate. Okay, so tokens, image tokens and text tokens are aligned in a single sequence, and they all get processed by a single transformer. Okay, that's attending the tokens kind of before, and the objective, pre-training objective, is just to simply predict the next token then in a sequence. Okay. The same says the paper is like a simple formula with like probability distribution, where the loss function is just like trying to optimize for the next token, and nothing really crazy going in here. They say that for that to work, they need a lot of data. Specifically, they had to kind of train for 6.7 epochs, so a lot of training took place for that work well. and they've obviously fine-tuned it and all for instruction following, for safety, and all those good things, so that the model could be used for the following task: image and video captioning, what we already use it for in that guide, visual question answering, and even image classification, for which you have to like attach another model hat, image classifier, and train the model, fine-tune the model for the appropriate data set containing those classes. Okay, but for question answering, for instance, you might want to ask, like, how come if the model accepts just a single image parameter? Well, it doesn't. It accepts text. It could accept text too. Okay, so that the model actually is trained to predict the next sequence. Doesn't really matter like where it starts. So you can, for instance, send this like initial image sequence as well as this like initial prompt sequence, your question, for instance, about that image. And the model will try to predict how to end it, like what to answer, basically, how to follow up on that question, okay? And provided that it's been trained on a series of questions like that, so it kind of responds to it, given the image, question, and answer, it knows how to do that, right? On a big data set, on a big volume of data, it will just as well respond to your query without much of a problem. But back to our guide, what is the rest of it that they're doing here? Let's see. So after they've downloaded all of the images, they print some of them out for a quick review. They download the model itself as well as its processor that comes with it. Then they prepare the input sequences by processing images that come along with captions with the transform function, okay? So those input sequences is going to be fed to the model for fine-tuning, so it predicts it. It gets better at predicting. And then they prepare the metric function, basically using the WER metric to calculate the similarity between predicted captions and reference captions. They prepare the model trainer, similar as we've seen before, okay? They kick off the training job like this, and once the model is ready, they just like test it against one of the image that didn't take part of a training set, obviously. So they fed this image to the model, and the model responds pretty much accurately that it's a drawing of a pink and blue Pokemon, though without telling its name. As per the brief history and core principles of vision language models, I would really recommend just 2 papers, and those 2 papers will give you a comprehensive outlook at the state of the things in the area of vision language models and multimodal language models. The first one is this. It's called Vision Language Pre-Training, Basics, Recent Advances, and Future Trends. Very interesting read. It's a long one, having about 100 pages long, but it's worth it. Highly technical, but they cover a lot of stuff, starting with different models architectures, explaining pre-training objectives. They compare models of different types with each other, showing what works better for which task, basically. They provide details about datasets and all, fine-tuning. They cover core computer vision tasks as well as video tasks, basically outlining how it's been evolving over time, what model works best for a particular set of tasks. Super insightful, super useful if you are in a research community or planning to do something, considering the model. This thing will reveal a lot of interesting details for you. So we'll have a look into it for that. There's another comprehensive paper that's just been released on May 17th of 2024. There's a survey paper where they cover multimodal large language models. A lot of the recent ones, okay, but they're focusing on the area of performance, because if you think about it, with an increase of data modalities, the requirements for the models and hardware actually increases too. So you need more powerful hardware to train them, to serve them. You need better optimization methods to train faster, more efficiently, right? Because the amount of data increases, so you need to be able to address that. So they cover different methods and optimization techniques in this very paper, the most recent ones, and also highlight some of the challenges, some of the things that researchers are looking into at the moment. So I'm gonna leave it for your home assignment. I'm not gonna cover it in this video because the video is gonna get like very lengthy. So, but there's another opportunity for us to follow up on. We're going to have a look into this paper now, and we'll learn a whole lot of interesting things about how those models function, how they work, what's happening under the hood. But really, we'll just consider some high-level stuff, architecture, core principles, what elements get substituted from model to model. We'll learn that. We'll also focus and explore some of the tasks, core vision tasks, and what models perform better than the others when it comes to certain tasks. And finally, we'll consider some video tasks as well that have good coverage in this paper. Let's start with a simple architecture of an early vision language model. And that is usually purpose for a single task. In this very instance, it's a vision question answering task, all right? That is under classification category, by the way. So the way it works is that you give an image question pairs, a bunch of those that comprise your data set, okay? So, then you have a model that consists of multiple things. First of all, there's visual encoder and text encoder. Visual encoder takes your images, converts them into visual representations in form of embeddings, right? Text encoder does the same to the text. Visual encoder doesn't take like entire images. There is a preprocessing block, and it splits images into smaller pieces so that the model has a better grasp of details in the image, right? So there'll be like smaller crops that's fed as sequence along with like positional embeddings of sorts, all right? And then there is a fusion model, the purpose of which is to get like cross-model representations, basically to map the text representations onto the portion of images. So the model understands how is it one thing is related to another, okay? And then finally, there's going to be a classifier. In this very instance, it's a vision question answering classifier to predict basically the answer. This picture outlines what we've just discussed pretty well. It contains all those main blocks, main elements, and they could be implemented by different technologies, different methods. In those old days, convolutional neural networks were a thing. They worked pretty well for a number of tasks. That's why you see it here. They used it for visual encoder, for text encoder. Some early transformers, I bet, were also available already. So they experimented with them. Researchers actually do like experiment and see what works better, right? That's the whole purpose of data science, in a way. So for the fusion, for the data fusion, they were using a couple of things with attention, without attention, intramodality. We'll look into those things as well. So, and there was an image classifier in order to make this whole thing work for that very single task, okay? So in this very instance, what they're doing is they're prompting a model to detect what kind of an object is this under a dog's paw, okay? So that by the nature of the question, the model, it tries to pay attention to this very piece of the image. Remember that I mentioned that image gets split into pieces, right? So more attention is paid to this very instance, and model is making a corresponding prediction. But the question could have been asked about, say, a color of the dog's fur or the type of leaves on the ground. And provided that it comprised, that information was a part of a data set, training data set or fine-tuning data set, chances are the model could have predicted it correctly as well. This is a new modern architecture of later models where they experiment with additional things such as patch embedding for image encoder. They also tried different attention methods such as merge attention and co-attention, but this old dot product method has just proven to be working well, so they continue using it in some later models as well. They've also come up with some new pre-training objectives, such as masked language and image modeling, image text matching, and this image text contrastive learning has become sort of a standard led by OpenAI with their very popular clip model. This is an interesting piece of writing too, where they explain how multimodal fusion works. For those standard dual encoder models like clip and align, it's a simple dot product method that works quite well. But others make use of a more sophisticated mechanism, such as merge attention and co-attention. For the first one, they simply concatenate text and visual features and fed them to the transformer block. For the co-attention, though, it's different in a way that those tokens of individual modalities, they sort of like attend each other. So the model has a better grasp of it on a deeper level. The goal of this chapter is to underline the weaknesses of older approaches that made use of a closed set of concepts, which limits models' ability to generalize to broader concepts, sort of, unless you fine-tune the model with additional label data, okay? So they justify a new method by bringing in a language piece to the language model in a way, right? Because turns out that language carries out the concepts better than just image embeddings. It's actually well illustrated in this picture. They call this setting computer vision in the wild. And it goes like this. Whenever there is a closed set of concepts, let's say you are training the model on a very limited data set that has pictures and labels associated with it. So in this setting, the model is able to identify only those particular concepts, those objects like a person or a dog. It could like detect them, it could segment the picture onto those pixels, right? But whenever there is an open set, so the model is exposed to language more, let's say, right? Same picture, right? The model is able to identify more, not just the objects, for instance, but also whether the person is standing or sitting. It just like extracts those concepts out of language, so to speak, right? Provided you've exposed it to enough data. They cover some video tasks too that are attributable to computer vision problem. They point out to a very early research from as early as 2011, 2013. But what are the tasks really? We've already seen a few. For instance, video retrieval, given the text, given the prompt, find me a particular video correspondent to this, or get me a video moment out of the video, for instance. There's another task for video question answering, which is a more challenging problem to solve. That's where you need to make use of a language model to augment the capabilities of a system. Okay, so it could be a multiple choice question, could be open-ended question where you can ask anything about what's happening in the picture. Video captioning is still trendy, still hot. A lot of research is done. A lot of research has been done in the area. We've seen examples with Pegasus 1 by 12 Labs and Gemini by Google. A general video model is not quite different from an image model in the sense that the same text features are used, the same visual features are used. It's just that you're adding this additional dimension of time. So instead of a single picture, single frame, there's a series of those, right? So you got to take it into account, but the goal here is to convert those frames, right? Which gonna be a combination of patches, probably the portions of the frames and the frames themselves into a kind of sequence embedding, right? That contains those representation, but you will also share it. You'll also put it in a shared embedding space along with textual representation, so the model has a better grasp of how they map onto each other. And there's going to be some additional like information, like positional embeddings in between, so the model can understand the temporal aspects of that sequence. As per the pre-training objectives, I really want to break down this one. It's simple to understand, pretty much straightforward. It's quite popular. It's called video text contrastive learning. Okay, it's been used by a lot of researchers. So what's happening here is that you calculate the similarity between video and text by a simple dot product. There is a function that can tell you whether video is similar to a particular text. Okay, and then you're setting up a challenge for a model to predict like a video text pair, similar pairs, given batch, a small batch of those. Okay, so let's say there's a whole lot of video text pairs and there's labels, so you know what's similar to what. So you pick a batch of those unique ones, and you're giving it to the model. So, and the model, you set up your loss function so that the model tries to find amongst the rest n squared video text pairs those that are similar to the ones in the batch. Okay, given that you've got a lot of labeled data, and there are data sets available for you with sources like YouTube and others, so you can structure your pre-training data in a way so they're like video text pairs, similarities, and you feed it to the model as a pre-training objective. Well, the model will perform better as the training goes on. And finally, I want to show you the data sets that I've used for training those models. Most of the videos actually come from YouTube. There's a bunch of data sets available with lots of videos taken directly from YouTube. So it's available there as part of the training data set, but only for research purposes. You can't use these for commercial purposes, whether you want it or not. Let's talk about tasks, tools, and methods. It's funny I called it this way, but whatever. So we kind of discussed the tasks already, the tasks that are available in the Hugging Face registry, right? And what's provided to you in various guides in there. There's a pipeline actually provided. The pipeline abstraction that's been available for like regular transformers. Vision transformers are an exception. And for the computer vision tasks, they have different categories of those, right? There's one for depth estimation, there's one for image classification, and so on and so forth. And to use one, it actually comes down to a few lines of code, right? You just download the model to the pipeline, you specify the pipeline object, specify the model that has to be compatible with that very pipeline type though, right? So the model has a head appropriate for image classification, for instance, right? And you can also kind of fine tune it and reuse that endpoint. And then once this object, the classifier, is available through the pipeline, you can just do inference like this. Very simple. Hugging Face has this auto train thing, which has been available for quite a while, and this is sort of an automatic way to do machine learning. Amongst all those vision tasks, they only cover image classification. And the way to do that, actually, there is a good blog post article on the topic written a century ago, right? So actually, it's a very good explanation of this thing. You basically create a project, you upload your data set consisting of a bunch of labeled images, okay? And then it suggests you a couple model candidates to select, you agree to train them, and this thing does its work, like fine-tuning, changing hyperparameters, optimizing it, and then at the end you are getting this accuracy metric amongst all those models trained, and you can select which one you want to kind of go forward with. Hugging Face also has this Timm library, which is the largest collection of SOTA computer vision models. Well, not all of them are SOTA anymore, but still, right? It's accompanied by an open source repository. All of it's sitting right here. Code of all of the models right there. There's optimizers and other stuff that's needed for fine-tuning and inference. Okay, if we follow to the model section and see how many models it supports, and every single one of them comes with a paper. Funny. So it's also has this training script, and they cover some of it with documentation, basically providing with a code snippet how you can leverage that. But it's basically a wrapper around a regular Hugging Face transformers library. But if you don't have to write a notebook every time you fine-tune the model, well, this thing is of help, I think. Microsoft's got their model covered very well. There's an entire cookbook written on the matter, how to use 5.3 model, their latest model with different services. We've already seen Hugging Face version of it. It's also available in Azure AI Studio. I actually found it there. I think I covered Azure AI Studio in one of my previous videos, so I'll look it up if you're interested. But it's just a part of a regular Azure cloud. You create this additional Azure Studio resource, and then you open it up separately. So the model will be available in the model catalog. You can open it up. It'll come in the form of this playground where you can interact with the model by uploading images. There's a button for it. You can communicate with it in the chat. Also found this LM Studio, which is a desktop application. You download it, install it to your laptop and interact with it. It plugs into the Hugging Face API, I suspect, and it has all of those levers and knobs. You can like interact with a model's registry. You can select the model, download the model, and run it for inference in a visual UI, which is quite convenient, I think, for a rapid test. For the demo, we're going to be using this. This is one of the latest work in the space of large multimodal models. We're going to be using the model LLaVA, which is Large Language and Vision Assistant. It's represented by University of Wisconsin-Madison, Microsoft Research, and Columbia University. These are the name of researchers. And it comes as a project already. A few white papers have already been written about it. There is code available. You can follow instructions and run the model locally, interact with it. There's a demo website powered by their infrastructure. You can play around with the model this way. And they also provide information about data set, what they've fine-tuned the model with. This model has a simple architecture. They've just connected a few things. They've used OpenAI's Vision encoder clip with an image resolution of 336 pixels square. They've replaced a linear projection layer with a multi-layer perception block, which is a neural network containing 2 layers. This one just has a better kind of representation of data of different modalities. For the language model, they've used Vicuña, which is a fine-tuned version of Llama on a shared GPT dataset. And that one has outperformed like regular Llama and got much closer to state-of-the-art LLMs like ChatGPT and Google Gemini. For the demo, I've taken the photo of an omelette I cooked this morning on a regular iPhone. I converted the picture to the JPEG format because the model only works with that one. I uploaded it here and simply prompted with how to cook this, expecting the model to recognize the meal and give me a recipe of one, okay? And it's done just that. It correctly recognized the meal of an omelette and even gave a few details of ingredients comprising it. And it's also given me a step-by-step instruction how to cook one, which is a very detailed guide, I think. Another experiment that I did is with this picture I took last week during the event in New York City with AI Talks. There was one guy talking about his open source project involving AI evaluation, and I've simply asked the model to explain all the pieces it sees in the picture, okay? It's correctly extracted those writing, those text projected to the wall that the guy was demonstrating, right? And it's correctly identified the purpose of this meeting, that it was a sort of a discussion, okay, not a presentation of such, where the guy was talking about a tool called AI Eval. This is an interesting one. This is a photo I took with my Meta glasses where I was approaching the crosswalk and was about to cross the road. And I was simply interested whether the model would tell me if it's safe to cross the road right now, right? So it's quite a responsibility I'm asking the model to take in this very instance. So the model like confused this guy, thinking that he appears to be pointing, indicating that it's safe to cross the road, though I'm thinking he's just like trying to catch a car, to get a cab. And then also the model wasn't able to identify any visible traffic signals still, right? Pointing that it's possibly not quite safe to cross the road at this very moment. So it's taking this defensive approach. It's clearly seen in this case, right? But if you look closely, there is a very, very kind of a little light over here. That is a light, permissive light, allowing you to cross the road, and the model has simply not been able to identify it in the picture. And the last test I did, which is a simple geographic test for world knowledge, is by uploading this picture with the World Trade Center in New York City. It's a notable building. Everybody knows about it, okay? So I'm simply asking the model whether it recognizes this object. What it responds with is that it's mistakenly thinking that it's Empire State Building instead. But it's correctly pointing that it is located in New York City. So the model has failed this test. And one last fun thing I wanted to show you guys is vision question answering with a video model this time from the same project, though LLaVA, and the model is called Video-LLaVA 7 billion parameters. I specifically made a short video about how I make coffee in the morning, and I honestly wanted to have a conversation with someone regarding whether I'm doing everything properly. In order to analyze the video, I put together this notebook following the instructions from the model card. They were just enough, work like a charm. The only thing I did is that I updated some dependencies and installed some additional libraries. But before we see the result of my experiments, let's watch the video first. It's 33 seconds long, and I sort of cropped it into pieces and then connected them together, and it came out as a Instagram story of sorts, right? So it's like a short enough for a model to comprehend, all right? So I'm starting the brewing process. I am frothing the milk, and then the next thing I do, I'm pouring the milk into the cup with the brewed coffee. That's pretty much it. Before I run the model for inference, I do a couple of things first. I'm specifying the function for extracting frames from the video as instructed. I'm downloading the model itself from the outline checkpoint. I'm also downloading the video processor of that very model from the same checkpoint. And those come as special classes dedicated for that very model, okay? The next thing I do is I am processing the video, specifying the path to the video. You can see that there are a couple of files of different quality. So I haven't noticed any difference in the results choosing either one. So it doesn't really matter for our simple test. So I'm processing that video clip into another object using that function. And that goes to the processor, video processor, along with the prompt to get the sequence for inference. The very first thing I did is I simply asked the model to describe the process in detail, and here's what it's come up with. It's kind of funny, to be honest. It goes, a person is seen pouring a milk into a cup using a coffee maker. What? Coffee maker? The person starts by pouring milk into the cup, okay, and then proceeds to add coffee to the cup. Why would I do that? The person then uses a spoon to stir the mixture. I never use the spoon, ensuring that the coffee and milk are well combined. Okay, that's general knowledge. The cup is then placed on a countertop. Okay, I did that. And the person takes a sip of the beverage. What? I never take a sip of a beverage until the beverage is made. So it is not simply true. And then I switch to the video of a higher quality and ask the model simpler questions to see whether it would handle those a little bit better, okay? I'm simply asking next time what the person did after turning on a coffee machine, and the response with that the person poured milk into the cup, okay? It seems to be correct. So, but the next thing I'm doing, kind of like following up on the flaws of the first experiment, I'm simply asking whether a person takes a sip of beverage and like when exactly, right? And the model confirms that yes, a person takes a sip of beverage from the cup after the coffee is done brewing, which is not true. After coffee was done brewing, I poured the frothed milk into the coffee from the pitcher. Then I'm testing the model's ability to detect some textual or numeric information in the video. And one of the things I'm asking is about the boiler's pressure. It responds with 1 bar of pressure, which is not the case. In fact, the video is a little blurry in that very instance, so you can't really tell. So that is what I'm expecting the model to respond with. I'm asking about the number on the display, which is this little timer, and it's possible to actually see that number. It was about 16 to 17 at the moment of filming. And the model says that the camera captured display of the coffee machine shows the number 100, which is not correct. Then I'm simply asking for the brand and the model name of that coffee machine. And the model does a decent job of correctly identifying that it's Breville, but it's mistakenly pointing out to the wrong model. Then I'm asking for the cost of that coffee machine. And honestly, I don't know what is the knowledge cutoff of that very thing, but I think it's way off, because that very model, even the wrong model it's identified, which is cheaper model than what I have, currently costs at like 600 or so. But it says that it's just 200, which is like totally off. So this model is okay. It's functional, it works, but it's not quite accurate. I wouldn't say it's done a great job at question answering with my video. But I haven't done enough experiments on the matter. Maybe you could try too and tell me whether it works for you. But I'm a little bit suspicious. It definitely requires a little bit more fine-tuning, some additional data tricks and all. And 7 billion parameters doesn't seem to be enough for the video model of such. So probably needs some work. I think we've done quite a good job, haven't we? I think we did. We got familiar with the latest multimodal vision models, commercial ones and open source ones represented by big cloud vendors. We explored Hugging Face platform for vision tasks and looked into some of their guides. We looked into the brief history of how those models developed over time and understood their core principles. We also found some of the useful tools to work with vision models locally and in the web. And finally, we saw some of the demos with the latest open source LLaVA model that is highly capable when it comes to pictures, but as we've learned, not as much with the videos. I think it's enough for a single video, and I'd love to hear your feedback or really any other comment you might have in regards to the content of this video. So just leave a comment about it, okay? And if you're working on something, especially if it's a video part, if it comes to processing video, extracting data from the video reasoning capabilities of various models, definitely contact me. I'd personally love to chat, to work more on it, to explore the space, and drop me a message, a private message in social media so that we can coordinate our meeting and have a productive chat about it, okay? So on that very note, I thank you so much for watching, and you'll hear from me soon. Goodbye.